we finished talking about temperature, what it is, just the average of the kinetic energy of molecules. We talked about heat, which is the transfer of that energy. We talked about how the properties of different materials actually affect how fast or slow or how much heat is transferred. Now we can actually talk about the types of transfers themselves. So heat's usually transferred in three different ways. You can have conduction, um, which is the transfer of heat through touching. So if you have a hot object and it touches a colder object, you're going to heat up the colder object. So this is transferred by touch. We have convection, which is specific to heat transfer through liquids or gases. Then we also have heating by radiation. And this is done by electromagnetic waves. And we'll talk about the electromagnetic spectrum a little bit as well. So let's start with conduction. Um, how well a solid object conducts heat depends on the bonding within its atomic or molecular structure. Okay. Over here, you can see this lattice model of conduction. And you have all these atoms. So maybe this is I don't know, block of iron or gold or something. I don't know. I have not counted the neutron or the neutrons to see what this is for the protons. So what's going on here is we have this sea of free electrons. So you can see all these electrons. And this is what's going to conduct. You're going to essentially get your energy transfer from these moving electrons. So you get these moving electrons that cause this. Specifically, just the loose outer electrons are what's going to cause the conduction. There's going to be several electrons that are still firmly in place in the atoms. So usually metals have the loosest outer electrons, and that's why you see so many metals that are really good conductors of both electricity and heat, as they have this cloud of loose electrons flying around in them. And those electrons are free to carry out collisions throughout the metal. So there's where you're getting your heat transfer. Right? Now, most liquids and gases are poor conductors in this way. So poor conductors that impede the transfer of heat are called insulators. Poor conductors or insulators are going to insulate whatever the heat is and not let it leave. So we've got like wood, wool, straw, feathers. Like if you have a feather boa, that's actually a really good insulator. And in this case, the outer electrons in the atoms of the insulators are actually firmly attached. Okay. And firewalkers actually use this fact when they do their trick of walking across coals. Wood is actually a really good thermal insulator, which makes sense because you can stick a piece of wood into a fire like a campfire, and the end of the wood could catch on fire, but you don't feel it in your hand. That heat doesn't transfer. You feel the heat from the flame, but you can still hold that wood. It's a really good thermal insulator, and it is slow to transfer heat, right? And we'll talk about how heat transfers through liquids and gases later. But for now, we're just going to talk about solid objects. So just like how firewalkers rely on the low conductivity of wood, this same idea keeps you safe if you put your hand in a pizza oven. So like you have your pizza oven here, And if you're not familiar with a pizza oven, essentially a big open oven with a fire in the back. And then if you stick your hand in there, it could be hundreds of degrees inside, but stick your hand in, your hand's fine. Don't leave your hand in there. So air is actually a very poor conductor of heat. And some of those insulators I mentioned on the previous slide, like the feather boa or fur wool, the reason that they are good insulators is because they trap those little pockets of air inside their construction. And that's actually what helps them be an insulator. Snow is also a good insulator. If you have a blanket of snow, it can literally warm the ground under the snow if you have a nice deep layer of snow. So when snowflakes form, they form little crystals, which by default those little crystals will hold a lot of air inside. So there's lots of trapped air inside. So when these collect and stack up on the ground, you actually get a lot of trapped air in there, and that's actually going to act as an insulator. You can look at some traditional Arctic dwellings like igloos. Um, they're pretty much shielded by the cold just from their snow covering. Animals in the forest will actually find shelter from the cold inside snowbanks and holes in the snow. You can see here this ice hotel in Canada. I have a link there if you're interested. You can see how deep the snow is, but it's essentially coated with snow on top, and I believe the whole thing is carved into a snowbank. So you can actually stay inside these if you have the snow built up right and deep enough, and it will keep heat from escaping. Now, when I say it keeps heat from escaping, keep in mind that the snow does not provide warmth. It only slows down heat loss. Okay. So it's not going to keep you super warm. It's just going to make you get colder slower. But it can be done. You can see it in nature all the time. This is where a lot of Arctic type animals will actually live and stay. Okay, let's think about this example. Why can you place your hand briefly inside a hot oven without harm? But if you are burned, or you are burned if you touch the metal sides of the oven. Well, when your hand is just in the air, you're fine because air is a poor conductor. But if you touch the hot sides of the oven, it's going to be like an instant burn because the metal, not the air, is an excellent conductor. Right? So that's conduction, basically heat transfer by touching. Let's talk about how liquids and gases do it. And this is liquids and gases transmitting heat through convection. Okay. Essentially, convection is just heat transfer due to the motion of the fluid itself. So unlike conduction, convection involves the motion of sort of blobs of matter. So think about a lava lamp. Right? So if you have a lava lamp, you've got these blobs. They heat up and they rise to the top, which pushes another one down, and you sort of get this cycle over and over and over. But we're thinking about just the blobs themselves, and that's how the heat's being transferred. That's what happens in the situation of convection inside of a fluid or a gas. Convection can occur in all fluids, whether it is a liquid or a gas. So you can see over here in A, looks like an outdoor shed. Here's the roof. Looks like they have a heater inside there too, right? So there's their heater. So what's happening is this heater is heating and stirring up the air inside this room. So you sort of get the circulation. You get essentially these blobs of air moving around. So this would be a gas. Then we also have convection working inside a liquid. So if you heat this pan of water, you're going to get the same thing. You're going to get all these little currents of convection, these convective currents in here, and that's what's going to transfer your heat around. So when your water starts boiling, when all those bubbles are rising up, that's when you're actually getting a lot of heat dispersion in your water on the stove. This would be a liquid. Now, when a parcel of air near the ground is warmed, right? So this would actually warm by conduction. You can see that here. And of course, that's driven just by the heat from the sun. So we'll talk about that type of heating later. So when a parcel of air near the ground is warmed, it expands and becomes less dense. Okay, so here's our parcel of air. Now, you know that if you heat something, whether it be a metal or anything, we've talked about this before, it starts expanding. So if air expands, it becomes less dense, and anything less dense, just like ice, will start floating upward. Okay, so our parcel of air floats upward. So this warm air is going to rise. Okay, well, it's going to take its heat with it as it rises. Okay, so this is a convection here. We're moving a blob of the material that is a different temperature. It's warmer, it's going up. So the rising air is then cooled as it expands into the slightly lower pressure space. So as it rises, the atmosphere is less and less pressure. You know that from flying. That's why you have to have a pressurized commercial aircraft if you're flying like coast to coast. So as we get higher, this parcel is going to expand. And as it expands, it's the same amount of atoms and molecules in there, but since they have so much more room to jump around, their temperature is going to go down. Okay, so the rising air is cooled and it expands and it fills more space. So as this happens, the initial energy acquired by the parcel of air on the ground is actually offset by its expansion. Okay, so that's why as it rises and expands and cools. That's why air temperature is usually lower at higher altitude. So your temperature, if we were to make a plot, let's see. So this is your temperature and this is your altitude. What's going to happen is your temperature is going to decay as you go up in altitude. Now you can see this from the window of a plane, or if you can see a long way and you can see a storm coming in, you get these convective clouds. So what happens is you start getting all this convection, right? And then all of a sudden you get a cloud because the temperature is cooling, making the cloud. And then what happens is because of the conservation of momentum, when you get to the top, this thing has all this speed, but there's no more buoyancy force to push it up. So it starts going out and filling up the top. And that's how you get these big anvil clouds before storms. So this motion will actually stir the atmosphere and produce winds. And it also essentially causes these convective currents. So these convective currents are the things responsible for creating wind. Some parts of Earth's surface, like land versus water, they absorb heat from the sun differently. And then as a result, the air near the surface is heated unevenly and convection currents form. Okay, and we can see that right here in this small figure. So in the daytime, the shore, so the land, is going to warm more easily than the water. Okay, we can see that here. The land 70 degrees, the ocean 65 degrees. Now the air over the shore rises and cooler air has to come in and replace it. So as this air heats up, it's going to rise. Okay, so here's our little air parcel. Now, when it rises, something's got to take its place. We can't just leave a vacuum there. So what's going to happen is that's going to pull in this cold air parcel to take its place. So you can see how over time this setup happens and you get this current. Okay, but then in the same place, as soon as the sun goes down, the shore is going to cool off quicker. But the water, remember, it's a really good insulator. So the water is going to pretty much stay the same. So in that case, the warmer air over the ocean is going to rise and the cooler air over the land is going to take its place. So here you see the land is now cool, but the ocean didn't change much. It went from 65 to 64. So now we're going to get some net convection over here. So our air parcel is going to rise. And then this colder air has to come in to take its place. So you'll notice that during the day, and you can see this in the campfire here, during the day you get onshore breezes, and then during the night you get these offshore breezes. So if you ever spent some time on the beach, maybe build a campfire, watch for this. You'll hopefully, if physics works out, you'll be able to see it. One extreme example of this sort of happening all at once is just steam coming out of the top of the pressure cooker. So my mom and grandmothers all did a lot of canned foods when I was growing up, so I got to see this a lot. But the whole idea is that when this pressure is releasing, you've got very hot steam down here at the bottom. But then because it's mixing with cooler air and it moving up and expanding, so you've got all these things happening at the same time, expansion and rapid mixing, essentially just a foot above where this super hot steam's coming out, you can just put your hand and it's essentially cold to the touch. However, if you were to put your hand down here at the bottom, you'd be burned. So just in the span of like 1 foot, you lose all of your energy due to rapid expansion, and you can actually see that in the water vapor. So this is the water vapor. The steam actually is down here. So a lot of people think that what you're seeing there is steam, but that's actually just water vapor. Steam's down there where you can't see it. So in cases of rising and expanding air, essentially the way you can think about this on a molecular level is essentially all these moving molecules, when they collide, they come out fast, like as they, let's do it this way, they come out fast from the pressure cooker, and then they start crashing into the molecules that's already slowed down that came out earlier. So essentially, you can think of it as like the bunch of people in a conga line. When the first person stops, no one else knows it. So then they all just sort of get jumbled up. So they eventually stop, but the first one might still get smacked and pushed away. But everything else back there, they're going to run into one another and slow down. So that's the whole idea of what's going on as the air cools and expands. So you have a incoming molecule and then a molecule that's been out for a while. So what happens is they do an energy transfer due to conservation momentum. So this one that came in fast is now traveling slow after the collision, and the one that was going slow is now traveling fast. So you sort of get the conga line effect as a gas expands. You can see that these vectors are actually shorter in the expanded version compared to the version of this gas where it just comes out of maybe some sort of hose. So maybe it's coming out this way, little puff with lots of energy, lots of temperature, high temperature, lots of velocity. Then as it expands, a lot of these actually stop moving as much. So let's think about this example. You hold your fingers beside a candle flame without harm, but not above the flame. That's where you get hurt. So why can you put your hand beside the flame but not above the flame? And if you remember, hot air travels upward by air convection. So since air is a poor conductor, very little heat travels sideways to your fingers. So um, conduction doesn't happen this way. What is happening is we have the rapid convective lifting and heating here. So this would be convection. This would be conduction. So you got two different types of heating going on here. Well, one good type of heating, one terrible type of heating. And that's why just from the flame of a candle, why you can get your hand really close to the sides, but not above it. Now, convection actually shows up a lot. So obviously it happens whenever there's fluids and there's temperature differences in the fluids. So this is what produces clouds in the sky, just like the steam out of the pressure cooker. It's essentially the same thing. It rises, causes water vapor to condense. So in addition to producing clouds in the sky, this is where we get our deep ocean currents from. I'm sure you've all seen the maps and heard people talk about how well, actually, we've talked about it. We've talked about the Gulf Stream moving warm water up to Europe. That's actually driven by convection. Convection is also a thing that happens deep within the Earth's interior. So actually, in the mantle, you sort of get these convective currents set up. That's where we get our lava traveling up to the volcanoes, that kind of thing. It also plays a large role in the sun. Accounts for solar flares. And you can actually see in the layers of the sun, we have an entire layer that we actually call the convective zone, where there's so much churning on the surface happening. All right. So that's everything we need to talk about for conduction and convection. Now, the last thing we need to talk about is radiation. So light energy from the sun passes through space. Light energy from the sun passes through space and gets to the Earth, passes through the Earth's atmosphere, and then warms the Earth's surface. So we talked about molecules transferring heat through conduction. We talked about the fluids themselves transferring heat through convection. So how does heat energy travel through empty space? That's what's weird here, because there's no medium between the sun and the Earth for radiation to transfer through. How does it do it? So clearly, since there's nothing there must be a third process. So there's some other process of heat transfer that does not depend on molecules. So this particular type of energy is called radiation. You can actually see radiation in so many different forms. Radio waves, so every time you turn the radio on in your car, that's a form of radiation. That same type of radiation is what you feel beside a fire. That's still same type of radiation, just a different energy, and that's just infrared waves. So heat energy. And then the same type of radiation, just at a different wavelength, different temperature, is actually what you see when you turn on a light bulb, that visible light. And you can see here in these little cartoons, the waviness of these lines changes. So here you have less wavy. Wavy, there we go. Then over here you have more wavy. So it turns out the waviness of these emissions actually determine what's going to happen and how you interact with these waves. And that's what we're going to talk about. So radiant energy is in the form of electromagnetic waves. we just looked at. This type of energy, okay, here we go. Here's the big list. This type of energy includes radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. And you can see they're all labeled here in order. We're going from radio waves, microwaves, all the way up to gamma rays. You'll notice that the wavelength here, we'll talk about that in a second. The wavelength, we start out with long, slow waves. So from here to here, long, slow. I don't want to call it slow because they technically all travel at the same speed. Oh, great. And now I can't erase. That's okay. I'll just mark over it. So we have long wavelengths. And then if you notice over here, by the time we get to the other side, we have short wavelengths. Okay, so all of these forms of radiant energy, they're listed in order of wavelength, as you see, from longest to shortest. And it turns out the longer wavelengths, like this one, that's related to a cooler temperature. Whereas if you have shorter wavelengths, that's related to a hotter temperature. Okay, now we know that a hot temperature, let's start with cold. We know that a cold temperature means there's low kinetic energy, and then a hot temperature means there's lots of kinetic energy. Okay, well, so a low temperature would be, we could call it cold. So we could say cold over here, low energy, right? Because that's not a lot of jittering in atoms. But then over here, we could have hot, high energy. So this is why when you go get an X-ray, they need a high energy X-ray machine to actually penetrate through your bones, come out the other side, and make the image, right? So this is why you have the high energy here. If you wanted to, work at a nuclear power plant, well, the nuclear power comes from very high energy radiation releases, right? So you're going to be looking at something like gamma rays. So here's the full spectrum starting from lowest energy all the way up to gamma rays, which is the highest energy. The wavelength of radiation is related to the frequency of its radiation. Okay, so now we have to flip this in our heads. So the frequency is the rate of vibration of a wave. So here we have these, as you can see from this girl wiggling this string. So this will be low frequency. Abbreviate. So a low frequency would be just a few waves happening over a given distance, right? So here's our distance. We'll call it X. So here we just have two peaks happening. Well, if only two of them happen in the space, that's a pretty low frequency occurrence. But a low frequency means a long wavelength. See how they're sort of inversely proportional? So this is a long wavelength. And if we look at the other one, where this girl just really gets this rope going, now we have four peaks in the same distance. So this is a high frequency. But even though it's a high frequency, it's now a short wavelength, as you can see here. Right. So what we could say is that frequency is inversely proportional to wavelength. Wow, it should be an H. There we go. And you remember this from previous conversations we've had where if frequency goes up, wavelength goes down. If wavelength goes up, frequency goes down, right? So if one of these goes up, the other one has to go down, and vice versa. If this one goes up, this one has to go down. So don't get wavelength and frequency confused. You just got to picture that wave in your head. If there's lots of peaks, then you know it's a high frequency, short wavelength. But if there's only a few peaks, then you know it's going to be a low frequency, long wavelength. So the cool thing about talking about frequency and wavelength is all substances at any temperature above absolute zero, because that's important. As soon as you get above absolute zero, stuff starts emitting radiant energy. So the peak frequency of this energy is directly proportional to the absolute temperature of the emitter. Okay, now let's think about what that means. So obviously, when something heats up, it doesn't just emit one wavelength. You might have some visible light, you might have some heat, you might have some UV light, but the peak frequency, things will have a peak frequency, and that peak frequency depends on temperature. All right, we can look at this. So here's our frequency. So we have, let's switch to black. So we have our frequency here. Okay, you'll notice that this first frequency is at 1600 Kelvin. Okay, well, if we increase the temperature to 2400 Kelvin, well, that's going to shift us to another frequency, right? So the frequency also goes up. It's directly proportional. Now, if we increase the temperature of this thing again, we're going to move up to 3200 Kelvin, and that, of course, will also increase our frequency. So as one of these increases, if peak frequency increases, the temperature of the object will also increase. If the peak frequency decreases, temperature must also decrease. So don't get that confused with the relationship we just talked about, where the frequency and wavelength are inversely proportional. So if you take an object that's just like, take just a regular old object, and then if it's hot enough, if you heat it up enough, it can actually start pushing this peak frequency into the range of visible light. So the whole idea is you can essentially, maybe your initial distribution is here, and this is your peak frequency. But if you add enough temperature, you can get a new peak frequency that's in the range of visible light. So anyone that's ever done any metalworking or watched someone do metalworking, when that metal lights up, starts turning red, that's because it's so hot, it's red hot. That's what's happening. You're raising this distribution up into the range of visible light. And you'll start with red and then go yellow and then go essentially white hot. So because different colors correspond to different temperatures, we can actually tell what temperature stars are. So stars are different colors due to their temperatures. So because let's talk about why we can see what we see here just in everyday life. So the surface of the sun has a high temperature, duh. It emits radiant energy at a high frequency. That means short wavelengths. Much of what it emits, so if you think about the distribution of its frequency and temperature, okay, so much of what the sun emits is actually in the realm of visible light. That's why we can see, because we get so much visible light from the sun. So by comparison, the surface of the Earth is relatively cool. So as it heats up, it's also going to radiate energy out. But it's going to be lower frequency, right? It doesn't have all the energy of the sun. So even though the Earth is going to radiate energy out, it's going to be lower energy. Okay. And it turns out that even though visible light is coming in from the sun, let's label it here, visible. Even though we have visible light coming in from the sun, we radiate infrared waves, or the Earth radiates infrared waves, and this is essentially called terrestrial radiation. So this has a big temperature, sun, obviously. The Earth has a lower temperature, duh, we live here. And that's because we have two different types of radiation going on. Just like the Earth, which is absorbing and emitting radiation at the same time, this actually happens with most objects. And we'll talk about that in a second. But first, all objects are continuously doing this. They emit radiant energy over a range of frequencies. That's why we have a distribution, not just a single value. So objects with everyday temperatures emit mostly low frequency waves. We saw that like with the Earth emitting infrared radiation, essentially emitting heat. But when this higher frequency infrared waves are absorbed by your skin, so we're emitting just regular old infrared radiation, but if we take in high frequency or higher frequency infrared waves, and those are absorbed by our skin, well, that's what you detect as heat. That's the sensation of heat. And a lot of times we'll call this infrared radiation just heat radiation. So if we wanted to, as we are emitting our own radiation, if we wanted something slightly higher to come in and heat us up, then sources would be like the sun, a lamp filament, embers, that kind of thing. This whole idea of just wanting emission to come in to heat you up, or thinking about other things emitting at all times, that's exactly how these thermometers work. These thermal infrared thermometers, you just point it at something, it'll read those waves and tell you what the temperature of the object is. Now, we can get to this question. If everything is emitting energy, why doesn't it finally run out of energy? So even though everything is always emitting energy, everything is also always absorbing energy. It's always a transaction. So you always have in and you always have out. Now, the wavelengths of these could change. The wavelengths of these change all the time, but you always have an in, you always have an out. So good emitters of energy are also good absorbers. And vice versa, poor emitters are poor absorbers. So for example, radio antenna. These things are made to emit radio waves, which is also a type of radiation. See here, these things are really good at emitting these big, long wavelength waves, but that also means they're really good receivers of radio waves. That's why we can communicate with these large antenna back and forth. They're made to do that. They're made to be really good emitters and receivers. All right, so the surface of any material, hot or cold, both absorbs and emits radiant energy. This is what we talked about earlier. This is what I hinted at. You always got something going in and something going out. So that's always absorbing, always emitting. If the surface absorbs more energy than it emits, it is a net absorber. Okay, so more energy coming in than it emits, long wavelength. Here's a net absorber. Now, what that means, if it's taking in more energy than releasing, its temperature is going to rise. On the other hand, if it emits more than it absorbs, okay, so lots coming out, just a little bit's going in. Well, if that's the case, then it's a net emitter, okay, and then the temperature drops. So it's just an accounting game. What comes in has to be compared with what's going out, and if there's more coming in than out, you're gaining temperature. If more is going out than in, you're losing temperature. So whether a surface plays this role of an emitter or an absorber depends on what the temperature is and if it's above or below the surroundings. So if a surface is hotter than its surroundings, it will be a net emitter. If the surface is colder than its surroundings, it will be a net absorber. Okay, so you just got to think about your background, so to speak. What's going on in the background? So this pizza over here is clearly hot. The area around it, the background, the surroundings, clearly is cold. Okay, so now that we have a temperature difference, since this is hotter, this pizza is going to be a net emitter. So what's going to happen is it's going to slowly get colder because it's a net emitter. And then the surroundings is going to slowly get warmer. Okay, so the table here would be a net absorber is warming up. Okay, yeah, let's see the net emitter. Okay, two more things. So absorption, which we just talked about, the table absorbing the heat from the pizza, absorption and reflection are opposite processes. Okay, so a good absorber, like that table, actually it would reflect very little radiant energy. So a surface made from a good absorber looks dark. So if you have visible light waves coming in on some surface, so this is visible. Now, if this is a good absorber, well, if it's absorbing all this light, you don't have any visible light leaving. So that's why it's going to appear dark. You don't get like nice bright images from it. So a perfect absorber, which we would call a black body, a perfect absorber reflects no radiant energy and appears completely black. And these are actually really hard to find out in nature, in the real world. Usually, there's no such thing as a perfect absorber. You have to do some sort of intervention to make something more of a perfect absorber. But the whole idea here is just a good reflector is a bad absorber. And if you think about this box here, notice this box is painted white on the inside. And we all know that white is a very reflective color. So it makes sense if we look at it through the top when lots of light is coming in, because we have lots of light, we can see it. We can see how reflective it is. We can see that it's white. We should be able to see through here, because there's light coming in, right? We should be able to see that it's also white and reflective. But because of the geometry of this thing, you can see as light comes in, it sort of gets trapped. Even though that white is a reflector, go. So all these sides are white. White is a good reflector. So essentially what's happening is, yes, reflection does happen off the white, but because of the geometry, it's hard for the light rays to get back out. So that's why as soon as you close this lid, this appears black. All the light's going into this hole, but because of the geometry, even though it's white inside, it's not letting the light come back out. So this is a really good absorber. And that's essentially how you can think of a good absorber. This situation here is sort of happening. All right, let's think about one more example here. So which is likely to be colder, a night when you can see the stars or a night when you cannot? So clouds or no clouds. It turns out it's probably colder on the starry night, so no clouds. And that's because when there's no clouds, the Earth's surface radiates directly to space. And then you get colder, essentially. But on a cloudy night, what happens? On a cloudy night, these clouds, they'll actually re-emit that energy back to Earth's surface. So this will be warmer. Usually, I mean, there's lots of meteorological effects that could happen, but um, generally, if there's a cloud or a cloudy night, it's going to be a warmer night just because those water molecules, which are insulators, are over you just like snow, and that's going to actually retain heat and keep some heat down near the Earth's surface. All right. Um, that's the last thing we need to talk about. This lecture was 3 different avenues of radiation, which would, or heat transfer, which would be conduction, convection, and radiation. So that's going to cover everything we needed to talk about in regards to heat and temperature. This is going to lead us into the next topic, which would be thermodynamics. Um, so this has been very much definitions and concepts. The next piece will be putting some math behind this, which would be the mathematics of heat transfer, which is simply just thermodynamics. And we'll talk about that next time. So in the meantime, if you have any questions, please let me know.